Hello, my name is Fernanda Sobral, and today I'm going to solve quiz number 2 from week 1 from the course of Physics 2. So the question says, if the air density were uniform, how high could the atmosphere be? And if it decreased linearly to 0 with height, take the air pressure at sea level to be 1 atmosphere and the air density equal to 1.3 kilogram per cubic meter. So what we have here are two parts. We have a general equation, which is this one, which applies for both of them. In one of them, when we solve this integral, which is in the first one, when the change is uniform, we have that P1 minus P2 should equal density times gravity times the difference in height, which should be y2 minus y1, where, as the diagram shows here, what we're trying to figure out is y2, where y1 and p1 are the pressure and level at sea level, where pressure equals 1 atmosphere, and p2 and y2 correspond to the end of the atmosphere, the highest part of the atmosphere. So once we have this, it is very simple to solve the first part, the first thing we're asked for. So we know that P1 equals 1 atmosphere, this equals 0, so this should not be taken into account. And, well, we have these values, right? So Y2 should equal P1 divided by the density times the gravity plus Y1. Am I right? And y1 is 0 as well. So this is simply the value, right? So P1 equals, we have to turn 1 atmosphere into pascals, which is 1.013 times 10 to the 5 divided by 1.3 times 9.81, and this gives us a result of 7.9 times 10 to the third meters, which can be translated into kilometers to 7.9 kilometers. So that is the answer of how high the atmosphere could be if the density of air would vary uniformly, which means that it is the same throughout the whole atmosphere. So that is for part 1. Part 2 is a little bit more complicated because it is asking what could happen if it were to decrease in a linear way. So if that were true, then we would have to define the equation that corresponds to how it varies. So we know that density should equal the density at the lowest point times 1 minus y divided by h. So this is a linear equation. And this can be substituted here, and once the integral is solved, it should yield the final result. So for this, we have that P2 equals P1 minus the integral from 0 to h of rho 0 times g times this expression right here, which equals 1 minus y divided by h, right? Times dy. So once we solve this integral, we reach the conclusion that P2 equals P1 minus 1/2 of density of air right here times g times h, right? So this equals P2. So from this, we can obtain the value of h, right? Which is what we're trying to find. So I'm gonna delete this right here so that I can continue. So this equals P2, right? So we know from this that h should be equal to a difference in pressures divided, this multiplied by 2, divided by the initial times g, right? So we know that P2 here should be 0. At the end of the atmosphere, there is no pressure. So this equals 2 times pressure at the lowest point, which is 1.013 times 10 to the 5 pascals, divided by the density at the lowest point, which is given before in the problem, and it is said to be 1.3 kilogram per cubic meter times 9.81. So this should yield a final height of the atmosphere of 16 times 10 to the third meters, which is equals to 16 kilometers. And that is our final answer for the second part of the problem. And that would be all. Thank you.